Hello, everyone. Welcome to the March 30th edition of Math 135. Couple reminders, you will have WebAssign due on Friday, and work on your project updates because they'll be due not this week, but next week. So today we're going to learn about what do we do when we want to construct confidence intervals when we do not know the population standard deviation. It's rare that we will know the population standard deviation, so we need a technique to handle what happens when this is the case. So in order to do this, we actually need to introduce a new distribution. So far in the class, we've mostly just dealt with the normal distribution, but today we need to learn about what's called the t-distribution. So if our population is normal, that's what it says right here. If our population is normal with a certain mean, then we can construct what's called the t-variable. That is, we're taking sample means from a normal population with mean mu, but you see here, this is the sample standard deviation. It's not the population one. And so because of that, we do not get a z distribution anymore. We do not get the standard normal because we've replaced the sigma, the population standard deviation, by s, which is the sample standard deviation. We say this variable has a student's t-distribution with n-1 degrees of freedom. That is the sample size minus 1. It's called student's t-distribution because the person who first wrote about it under a pseudonym student. Okay, so this is the t-distribution, and we should take a look at what the graph looks like. So the black line is the t-distribution with 3 degrees of freedom. For us, that would occur when the sample size is 4. The blue curve is the t-distribution with 5 degrees of freedom. For us, that would occur when the sample size is 6. And then the last curve is actually the standard normal. So there are several properties of the t-distribution that you can observe by looking at this. First of all, the t-distribution has its peak over 0, just like the standard normal. It's symmetric, that is, you can flip it around, it looks the same. And last but not least, as you increase the degrees of freedom, you see that the t-distribution is getting closer and closer to the standard normal. It means that when our sample size is big, the t-distribution will look a lot like the standard normal. So this summarizes many of the things that you'd want to know about the t-distribution that we just talked about. It's symmetric about the mean. There are a lot of t-distributions now. There's infinitely many. In fact, there's one for every sample size. So you see, it depends on the degrees of freedom. So there's a t-distribution with 1 degree of freedom, 2 degrees of freedom, 3 degrees of freedom. There's a different t-distribution for every single degree of freedom. And then as the degrees of freedom increase, the t-distribution gets closer and closer to the standard normal. And last but not least, the area under the curve is 1 because of the fact that this is a probability distribution. So we need to practice looking up some values in the t-distribution table. It's going to look different than the ones we've dealt with so far. This is what the t-distribution table looks like. And you see that it's a little bit different. We'll take a look at it a little bit more in just a little while when we need to look up some critical values. But you can find it in the appendix. Okay. So table 4 in the appendix is where we use to find critical values. Critical values are values for t, so that the area between TC the area between TC and negative TC is C. So for example, if one second. If C were equal to 0.95, what this is telling us is that the area from T of 0.95 to negative T of 0.95, the area here is 0.95. All right, so it works a lot like it did in the case of the normal distribution. However, it's going to depend on the degrees of freedom. So let's look at this table and find T 0.95 with n equals 7. So one thing you're going to want to observe here is that when n is 7, this tells us that we have n minus 1, which is 6 degrees of freedom. So in the table, we care about degrees of freedom, not the sample size. So let's go to our table. And what we see is, okay, we're interested in C equal 0.95. That's this part right here. Oops. Let's see, let's annotate this. So 0.95 is right here. And we have 6 degrees of freedom. That's right here. And so we see that that's telling us that our T of 0.95, when we have 6 degrees of freedom, is 2.447. All right. So that is the critical value there. So I want you guys to do a different example. I want you to find when the sample size is 11, I want you to find T of 0.90. So go ahead and do that. All right, now that you've had a chance to do that, you know that we have 10 degrees of freedom. And that's right here. And we have T of 0.90, and so that would tell us that our T of 0.90 is 1.812. All right, so now you have a pretty good idea of how to calculate these critical values, which you'll need for our confidence intervals. All right. So computing a confidence interval is basically done the same way that we did it before. We have to construct the margin of error, that's E. So the margin of error E is basically got the same formula as before, except we have the sample standard deviation. But everything else basically looks the same. So the entire process you learned before is going to be repeated. So the only difference now is that if I have a sample, I need to calculate the sample mean, and I'll need to calculate the sample standard deviation in order to construct these confidence intervals. All right, so what we're going to do is we need to know one of two things about our population. Either our population has to be normal or the sample size has to be at least 30. There are some ways to relax these conditions, but we can talk about that another time. So what we're going to do is we're going to look at some data about wildfires in the US, and we're going to construct a confidence interval of them. So let's take a look at the whiteboard. Okay, and we're going to construct a 95% confidence interval for the number of wildfires in the US annually. That is, what's the average number of wildfires in the US each year? Okay. So let's take a look at our Excel file and take a look at this. So this is the number of fires, and we see that n is equal to 33. The sample mean we can compute using the command average, and the standard deviation we can compute using equals stdev.s. All right. So let me record this on our whiteboard over here. Okay. So on our whiteboard, we can write down that in our sample, we had a sample of 33 years of wildfires. The sample average was 71,163 wildfires, and the sample standard deviation was 15303.71. All right, so we want to construct a 95% confidence interval, so we need to know the degrees of freedom, and that's 32. So we need to find this in our table. So we go to our normal table, and we notice that there is no 32 in here. There is no row with 32 degrees of freedom, so we go with 30 instead. Whenever the number of degrees of freedom is not in the table, just go with the one below it. And we're constructing a 95% confidence interval. So that should be right here. It means that our critical value for this problem is 2.042. Okay. 2.042. That's our t of 0.95. Okay. So now we need to calculate our margin of error, which should be equal to this lovely expression. So go ahead and compute what that's equal to. I think what you'll find is that it's roughly equal to 5,439.96. Okay, so what's our confidence interval? Our confidence interval is from x bar minus e to x bar plus e. So we need to compute what these are equal to. All right, so I know it suddenly popped on the screen, but what you should have gotten is that we're just going to assume that the margin of error is roughly 5,440. So we found that our 95% confidence interval is from 65,723 to 76,603. So how do we conclude? So we are 95% confident that the average number of wildfires per year in the US is between 65,723 and 76,603. That's a lot of wildfires. Now, we don't actually know if the true average is in that range. but we're still pretty confident that there are tens and tens of thousands of wildfires on average every year. Some years there'll be more, some years there'll be less, and that's fine. We're asking about what's the average number. So we're 95% confident that it's in this range. All right, so now let's do another example, and let's actually look at the number of acres burned each year by wildfires in the US. I know today's a real cheery topic. So let's construct a 90% confidence interval for the number of acres burned in the US each year on average by wildfires. Okay, so we need to get some information. We need to know what's the average number, our sample average, what's the sample standard deviation. The sample size is going to be 38.3 again, and we're going to want to know what's our critical value. Well, let's go to Excel. And on the sample mean. And the sample standard deviation. Okay, so let's go over to our whiteboard and record this information. So with our Excel file, we saw that the standard deviation was 2781864. That's a lot of acres. And the sample mean was 4961676. All right. So now let's go to our table and find the critical value. We know that 32 is not in this table, so we just go with 30 degrees of freedom. A confidence level of 90% gives us a critical value of 1.697. So 1.697. 1.697. All right. So I want you guys to construct this 90% confidence interval. So pause the video and go ahead and work it, and then I will work it as well. All right, now that you've had a chance to do that, we find that the margin of error is t of 0.90 times s over the square root of n, which should come out to be about 8.21790. Okay. So we need to construct the confidence interval where we have x bar minus e and x bar plus e. Okay, I think what we should have gotten is 4139886 and 5783466. Okay, so what is this telling us? We are 90% confident that the average annual number of acres burned by wildfires in the US is between 4139880, so that's like 4 million, and 5783466. It's almost 6 million acres. That's a lot of acres. And so we don't know for sure whether that's right or not, but we're pretty confident that we're looking at millions of acres, on the order of 5 million acres, every year on average burned. Some years will be more, some years will be less, but on average, we think that's about how much is burned. So in a given year, the wildfires might be really big, they might be small. It's hard to know. But if you're planning a budget for how much should I support my, wildfire fighting task force, on average, budget for about 5 million acres a year with a pretty big range. All right, so let's go back to our PDF. We've had some chance to use this now to compute some confidence intervals. All right, so as a summary, here's what you want to do when you're constructing a confidence interval. You need to ask yourself, okay, how do I find the margin of error, E? So the most common is that you do not know the population standard deviation, so you want to use a t-distribution. However, this requires you to know one of two things. Either your sample size is your sample's coming from a normal distribution, or your sample size is 30 or more. The second situation, which almost never happens in practice, is that you know the population standard deviation, and then you use the method we used before. So if in doubt, here is a table that tells you what to do. If you know the standard deviation of the population, you use the standard normal table. If you don't know the standard deviation, you use the t-distribution. Let me know if you have any questions, and I will see you all on Wednesday.